Hello everyone, today my group and I will be talking about our final Signals and Systems project. We created an analog synthesizer. Here you have Articam, with me Ashik Ali and Paul Krusel. So the introduction. In the music industry, there's a wide range of instruments available to create different notes and sounds. The only problem with this is you need to have the physical instrument with you to play this. In order to solve this issue, artists usually have a device called a synthesizer, which is pretty much a keyboard with a bunch of buttons and potentiometers, where you can vary the tones and get different instrument notes. So, to summarize, the goal is to build a synthesizer, make it customizable, and have the capability of varying the tones, and also make it easy for anyone to use. Here's our system diagram. Here's our system diagram plots. You have your audio oscillator, which is above 100 Hz. It starts with a square wave. You integrate it and get a triangle wave. And then you also have the low frequency oscillator, which is usually below 20 Hz. It also starts as a square wave. Then it gets converted into a triangle wave. Then those two things are combined together by subtracting in PWM mixer, which is known as the pulse width modulation. Then it spits out the square wave into the low pass filter. Low pass filter goes to the amplifier and then into the speaker. Here's our actual system diagram plots. As you can see, it did what we wanted to do, but the low pass filter was a little funky. We'll talk about it later on. Here's the main circuit diagram. In number 1, we have the audio tone oscillator. Number 2, low frequency oscillator. Number 3, the PWM. Number 4, low pass filter. And number 5, the amplifier, which later goes to the speaker.
So the audio tone oscillator is the part that creates the actual tones, the different tones. This starts by creating a square wave and then changing its frequency using the buttons and resistances pressed. And then the square wave is sent into an integrator, which integrates it and spits out a triangle wave. The oscillatory frequency that actually chooses the note is 1/2 RC, and you can hit up to 3 octaves generally. And this is a picture of the audio tone oscillator actually working. You can see the square waves turn into triangle waves. And so the low frequency oscillator is similar, except we have a constant resistance. You don't change it with different buttons. This is in charge of the low frequencies that are then later on mixed with the high frequency signals. It does the same thing. This is an example of the low frequency oscillator working. You can see that it has lower frequency square waves that are turned into lower frequency triangle waves.
This is our PWM that we have incorporated. It serves as a purpose to generate a pulse which features the synthesized tone. So from the previous two sawtooth waveforms that we have, this will generate a square wave output, and in return this is a much more stronger signal than 2 square waves subtracted. So as such, the PWM balance in a sense helps to sweep the pulse wave of the tone oscillator. This is just the waveforms of the PWM. So in place we have the state variable filter, and we're trying to achieve the low pass filter output as such with 2 high resistance potentiometers, which enables us to get a low cutoff frequency. That's our transfer function right there. So the 2 high resistance potentiometers allows us to alter the timbre, where it replicates different instruments with the same input frequency. However, we have encountered some issues as shown in the next slide, where the waveforms doesn't look similar to what we got from the PWM, which was somewhat like a square wave. Right here we have a rectified sinusoidal waveform. So from here it will be passed on to the amplifier, and it's basically a non-inverting amplifier which goes by the formula of 1 plus R2 over R1. From here on it goes on to the speaker.